Welcome to the presentation of our work, The Curious Layperson, Fine-Grained Image Recognition Without Expert Labels. This work is done in collaboration with Laina, Rupprecht, and Andrea Vedaldi from the Visual Geometry Group at the University of Oxford. Humans are naturally capable of understanding and describing the appearance of novel objects, even when lacking the expert knowledge to recognize them. For example, imagine a group of novice bird watchers walking through a forest observing birds. Even when they spot a bird they cannot name, they are still able to describe its visual appearance relatively easily. With this basic capability, it is then possible to consult field guides to find potential matches and eventually identify and find out more about the bird observed. Similarly, while searching the web using descriptions or keywords, retrieved results often include documents from online encyclopedias such as Wikipedia or other expert resources that help us identify the target object. For example, Wikipedia articles about birds also describe their typical appearance, as you can see here for the scarlet tanager. The ability to retrieve and verify such information against real-world observations enables us to learn more about a field without being experts in it. However, the current machine learning systems do not work this way. Typically, we train classification models on large amounts of data that have been annotated with precise ground truth labels. Different from simple visual descriptions, annotating images with expert labels such as bird species is much harder and requires field knowledge from ornithologists or citizen science projects. Most prior work has used these expert annotations as training data to learn models for fine-grained visual categorization in a supervised manner. In this work, we assume no access to image databases with expert annotations and instead use only pairs of images and descriptions, which we refer to as non-expert or layperson's annotation, since they can be crowdsourced or otherwise collected without specific domain knowledge. For example, it doesn't require any special knowledge to describe the first bird as small and red with black wings, while labeling it as a scarlet tanager is very difficult for a layperson. The difference between how humans approach this problem to how we train current models motivates us to introduce a new task. Hence, we propose a novel problem that utilizes images and class-agnostic non-expert descriptions to classify the images by retrieving the corresponding entry from a corpus of expert documents. We call this task Clever. To solve this task, we propose a method that we call fine-grained sentence matching, FGSM. We will now explain how the FGSM can be trained only using non-expert descriptions. The FGSM model tackles the problem at sentence level, comparing an image description to each sentence of the document. We design it as a Siamese model, which takes as input a pair of sentences and outputs a similarity score. The parameters of the sentence transformer T and the linear network phi are shared across the subnetworks. We train the FGSM in two stages and start by initializing the BERT encoder with the weights obtained from the sentence BERT model, which has been pre-trained on a large general-purpose text corpus. However, due to the setup of the problem, we do not have pairs of descriptions and their matching document sentences. We thus design a proxy task that allows us to train the FGSM with positive and negative sentence pairs. We automatically create a dataset of positive and negative sentence pairs based on image descriptions alone. As we have multiple descriptions per image, we create a positive pair by sampling two descriptions from the same image and a negative pair by sampling descriptions from two different images in the dataset. This trains the model to score whether two descriptions talk about the same or different objects, and fine-tunes the BERT encoder to the subtle differences in the visual descriptions. However, the current model is trained only on image descriptions and do not work well on expert documents, as the language and content often strongly differ. So we introduce a second training stage to reduce the domain gap between the descriptions and the expert documents. We freeze the encoder and reinitialize the FC layers. This allows us to pre-compute all the sentence embeddings, which greatly reduces the memory consumption and allows us to use the expert documents in the second stage. To best incorporate the documents into the training phase, we create a second dataset. As the expert documents contain a lot more information than visual descriptions, for example, information related to bird sounds or habitat, we want to train our model to not only recognize positive and negative pairs, but also neutral sentences that do not contain any matching information. Thus, the second stage of training uses three labels. Similar to the previous stage, we use two descriptions from the same image as a positive pair. But now we split the pairs of descriptions from two different images into two groups, neutrals and negatives. A pair of descriptions with the same noun but different adjectives is a negative example, whereas one with no attributes noun in common is a neutral example. The intuition is that two sentences with common nouns can be assumed to describe the same parts of the object, and thus different adjective means their appearance is different. Two sentences with completely different nouns likely talk about different parts and do not give supporting or contradicting evidence. Finally, we use the documents themselves for in-domain regularization, which we will describe next. The domain adaptation regularizer is based on two inductive biases and operates on the level of documents instead of sentences. We compute the matching score between a description and a whole document as a sum of scores of all the sentences in the document. Positive matches increase the score, negative matches decrease the score, and neutrals are ignored. We can then use a simple softmax operator across document scores to obtain matching probabilities for all documents. The first inductive bias is encoded in the first term and encourages that each description matches only to a single document by concentrating the probability mass on a single document. The second term encourages the predictions to be orthogonal so that the matches are distributed uniformly across the corpus. This uses the fact that in small random batches, the probability is high that every image belongs to a different class, which avoids the situation where some documents are never matched to any image. We evaluate our model on cup dataset. During evaluation for a given image, we first generate descriptions using a captioning model that has been trained on simple image caption pairs. Critically, please note that the ground truth descriptions that the model is trained with do not contain any named bird species. To increase the diversity of the object parts which are described, we generate multiple captions per image using beam search. We then turn to online expert resources to obtain one document for every class in the cup dataset, and the goal is to retrieve the most relevant document. Using our learned FGSM, we score each sentence in each document against all image descriptions and average all scores to compute an overall score for each document. The top ranked document assigns its class label to the image. Here we show some qualitative results. Please note that the images for the documents are just for illustration purposes and are not used for retrieval. We observe that even when the top scoring candidate is not the correct class, the visual appearance of the bird is often very similar to the target class. This shows that our FGSM has learned to match descriptions with documents based on visual attributes, even if the exact retrieval is difficult for some visually similar species such as warblers or as in the last row for all black birds. In the paper, we also show results on the Oxford Flowers dataset with similar performance. We hope that Clever will become an interesting challenge for the community to train algorithms on easily available non-expert data. A comprehensive quantitative evaluation, more baselines, and comparisons can be found in the paper. Thank you for listening.